Hello, I wanted to have an example problem available for a continuous distributed load. I'm going to be doing this problem. This is 4-159. The difference between this problem and the other example problem I created is that this one has an equation for the distributed load, whereas the other one we used geometric shapes to find the area under the curve. So let's go ahead and get started. It states the distributed load acts on the shaft as shown. Determine the magnitude of the equivalent resultant force, specify its location, measured from the support A. So we know our point that we're interested in. The point we're interested in is A, right here. And you notice that we have a loading function. That loading function, we have the function is given to us in terms of x, and it's in pounds per foot. So what we need to figure out, we are given everything in the picture, and I'm going to go ahead and write out my loading function. It's equal to 2x squared minus 8x plus 18 pounds per foot. We are also given some magnitudes here. Now, because we have an equation, those are not very important to us. The 28 pounds per foot, that's just showing us the value of this function at -1. If we plug that in, if we plug -1 into this function, you're going to see that we get 2 plus 8 plus 18, which turns out to be 28. So really we can get all of that additional information that's included in this diagram just by plugging values in to our equation. So for this, we're not actually going to use any of these. They're given here, and it's nice of them to do that, but they're not needed because we have our function. And some students see that as additional loads, and those are not additional loads. They're just showing us the critical points of that loading function. We're supposed to find the resultant force, which we call Fr, and the distance, x bar, from A. Okay, so let's go ahead and get started. We know that Fr is going to be equal to the sum of all of the forces. In this case, we have a distributed load, and so that's going to be equal to the integral over the length of the loading function, which is in terms of pounds per feet, times a little tiny piece of x, which would be in terms of feet, so we'd end up with pounds. That's going to be our equation for the loading function. Let's go ahead and solve that first. Resultant force is going to be equal to the integral over the length. I have this little L here. That just means we have to go over the entire length of the shaft. In this particular case, notice that A is at -1. That means we have to have -1 as the bottom of our range for our integral. Then at B, we're all the way at 4. So we're going to go from -1 feet to 4 feet. -1 feet to 4 feet. Our distributed load function is 2x squared minus 8x plus 18 dx. Take that integral, we're going to end up with 2x cubed over 3 minus 8x squared over 2 plus 18. I'm sorry, plus 18x. And we're going to evaluate that from 4 to -1. So that's going to end up being, first plug in the 4, 2 times 4 cubed over 3 minus the 8 divided by the 2 is just going to be 4 times 4 squared plus 18 times 4. Okay, then we're going to subtract with -1 in there. We'll have 2 times -1 cubed over 3 minus 8 times -1 squared over 2 minus 18. Notice I plugged in the -1 for the x there. That's where I got the minus sign from. Okay, just a simple calculator exercise, and we end up with the resultant force as 73.33. And what are our units? Well, they're pounds per foot times feet. The feet comes from the x. Obviously, the feet cancel, and we end up with pounds, which was what we were hoping for. Now what we're going to do is we have to figure out where that loading can be placed to have the same moment about A. So we want to find the moment caused by that distributed load. In order to do that, we have to consider the moment of one infinitesimally small force within the distributed load, and then use that in the integral. To do that, I'm going to draw one of those arrows. Let's just pick this one. Okay, if I draw that arrow, we know what the loading of that's going to be. The loading is always the same. It's going to be whatever that equation gives us at that particular x. So the loading is going to be Wx. But now we have to figure out the moment about A, which is going to give us that loading times the distance from A to that loading. Well, the distance from A to that loading is going to be 1 to get from there to the w-axis, and then another x to get from the w-axis to that particular loading. And that's going to be the same for each arrow. Notice that nothing would change. If we're on the left-hand side of the w-axis, that still works, because it would be, let's say, -1/2 plus 1, which would be 1/2 away, which is what we're looking for. So if I put it right in the middle here, we'd have an x value of -1/2 plus 1, which gives us 1/2, which is the distance we would want. So that means for each one of these, our moment is going to be the loading times x plus 1. So now what we need to come up with is we need to come up with an equation for the loading of each one of those arrows. And that's pretty easy. We're just going to take our distance, which is x plus 1, and multiply it by our loading, w sub x, which is going to be equal to x plus 1 times 2x squared minus 8x plus 18. Multiply those two together and we get an equation for the moment. That's going to be, I'm just going to FOIL it out here, 2x cubed minus 8x squared plus 18x. Now with the 1 multiplied would be 2x squared minus 8x plus 18, 2x cubed minus 6x squared plus 10x plus 18. And what are our units? Well, we have pounds per foot times foot, so this would be pounds. Now, to find the moment, the resultant moment, we know that's our moment equation. We just have to sum up all of those little moments. To sum up, we're going to use the integral, same bounds, because we're going on the same length, of our new equation, and you can see that the units are going to work out. We get the pounds from our equation, and we get the feet from our x values. So it's going to be foot-pounds, which we would expect for a moment. So let's go ahead and evaluate that. 2x cubed. Oops. It's like I made a mistake there. It was supposed to be x cubed on the first one. So it's really 2x to the 4th. Over 4 minus 6x cubed over 3 plus 10 x squared over 2 plus 18x. We're evaluating that from -1 feet to 4 feet, which is going to give us 4 to the 4th over 4 minus 6, 4 to the 3rd over 3 plus 10, 4 squared over 2 plus 18 times 4, and we're going to subtract from that 2 times -1 to the fourth over 4 minus 6 negative 1 cubed over 2 over 3 plus 10 negative 1 squared over 2 plus 18 times negative 1. Okay, again we have a calculator exercise here. I'm going to end up solving that in the moment. And I should put an A in here just to remember we're taking it about A. The resultant moment about A, that's going to be equal to 162.5 foot-pounds. Okay, so we know that we need a moment about A of 165.2 foot-pounds. And we know that if we want to use the resultant moment, which we already calculated, it's up here, 73.3 foot-pounds, we need to figure out an equivalent system that is going to be our shaft. Our shaft, this is point A over here. It's got a, looks like bearing supports at A and B. And we know that we're going to put our distributed load somewhere. We just need to know where. Well, if we're going from point A, we know that the moment about A has to be 162 feet. Well, the moment about A is just going to be x bar, distance from A, multiplied by, let me just change that to green, x bar multiplied by that resultant force. And we know that that has to be equal to 162.5 foot-pounds. Let's quickly check our signs. So when I did that integral, I was keeping the moment as a positive, but if you look at the positive, you look at the actual moment, the forces will be pointing downwards. If you put your thumb of your right hand on A, point your fingers towards the forces, they would tend to bend them back. So I really should have had a negative. And now I'm going to go ahead and solve for x. X bar is going to be negative 162.5 foot-pounds over negative FR, which is the same thing as 162.5 foot-pounds over 73.33 pounds. Our x bar would therefore be 2.216 feet, or to 3 sig figs, 2.22 feet. And that is the distance from A. So that means that we should be putting our resultant force somewhere here in order to have an equivalent system to the above. And that's going to be a distance of 2.22 feet from A. Okay, hopefully that was helpful on how you solve a distributed load problem. There is an equation in the textbook that basically gives you x bar exact same way we were doing it, but it gives you the entire thing, which is the integral over the length of wx dx over integral over the length of x wx dx. This is very similar to what we did, but this problem is making an assumption. It's making an assumption that the point you're interested in is always x away from the load. In this particular problem, they had given us a w-axis that was not on A, and that's why we modified it just a little. So make sure that you always understand the problem that you're doing before you blindly use an equation. That's why we used x plus 1 instead of x, is because our w axis was 1 away from the point we were interested in. Alright, I hope that is helpful to you. Let me know if you have any questions.